Let me preach to you a little bit. I've been putting these quotes up here in the morning. I forgot to talk about yesterday's quote, but it's pretty self-explanatory. This means a lot to me, and I share this with students any chance I get. Dude said, don't ask yourself what the world needs. Ask yourself what makes you come alive and go do that. Because what the world needs is people who have come alive. And I kind of started out asking what the world needs. I did my undergraduate in electrical engineering, and I had no clue what I was doing. People were like, you should go to college. And I was like, okay. Right, like I had no idea. And I didn't know what I was going to do. And they were like, you're good at math. You're like, you could be an engineer. And I was like, okay. And really just not sure what I wanted to do. But I looked at like, what does the world need? And I was like, yeah, electrical engineering. Like everything is electrical and digital. And yeah, I can do that and make money and blah, blah, blah. So I went to school for that. And as I learned more about the world and about my life and about society and everything, I was like, I don't think that's my thing, right? Like I was okay at it, I guess, but it didn't make me feel alive, right? Like writing computer code, or like wiring circuit boards or anything. Like I wasn't stoked. I didn't feel like that was, like I'm gonna die. Like what am I gonna leave? What's my legacy I'm going to leave behind on Earth? And is it going to be that like I made some electronic things? And I was like, nah. And I wanted to make a difference in the world, and I wanted to make a difference in people's lives. And I figured that the best way to do that for me would be through education. So I don't believe that people would do stupid stuff, like lying, cheating, robbing, stealing, murder, and wars, and just all the social ills that we experience on the planet. I don't think people do that. I think they're doing what they think is their best idea, right? And I don't think people would do stupid stuff if they knew better. And I was like, well, I want to help people know better. So I'm a teacher. So whatever that is, though, find what makes you stoked and do that, right? Because we need people to be stoked about life. We need people that are excited to do what they're doing. And when you do that, everything else works out, right? So if you're like, well, I need to make this much money, so I need to get this job, and you hate your job, and it sucks, like you're not doing anyone any favors. So whatever you're into, and you might not even know yet, and that's fine. I didn't know, so I was graduating, right? It was my senior year of my undergrad, and I was like, I know what I want to be when I grow up. So whenever that hits you, some people might know, some people might not have any clue, but think about what makes you excited. Like what do you want to give to the world? What makes you feel most alive and passionate? Like, are you super stoked to help others? Like when you help a friend out with something, are you like on top of the world that day? Or like, I don't know, maybe you like horses or something. You train horses, you ride horses, and you just love it. Or whatever it is, take note of what you're excited about in life. And keep that in mind when you head forward in the future. And really, you can't mess it up. I mean, going to college is neat because you'll just meet a whole bunch of people that are doing neat stuff in the world. And you'll be like, oh, this is really neat what you're doing, or I never thought about this. And you'll see things and learn things, and you'll end up finding your path if you don't know it already, right? At universities and things, there's a lot of people doing really cool research where you're like, what? I didn't even know that was a thing. And so just go, right? So I don't regret that I have an engineering degree. And that's the funny thing. There's everybody, it seems like, people have degrees in all kinds of stuff that isn't what they do, right? Like one of my very good friends, she's a software engineer. She works for Blizzard Entertainment, the gaming company, right? Like Diablo and World of Warcraft, all that stuff. Like she writes code for Blizzard. It's like her dream job. She has a degree in political science, right? Like my stepdad has a degree in sociology. and he's like a machinist and sells motorcycles and stuff. You know, like whatever. Like go get a degree in something. But don't forget about your passion and your joy and what makes you stoked to be alive, and make sure you're doing that. Yeah? Okay, dismount. Soapbox. Let's talk about math. Okay, what happened yesterday? Jack, what did we do yesterday? What was that all about?
We were like looking at limits, and also there's this big paper covered with limits.
Yeah, limit. Okay, Mauricio, what is a limit?
It's like what f of x equals when x approaches a certain limit. Like what's the y?
Does it equal? Does f of x
It
equal?
approaches.
Yeah, we're approaching. So the limit is a thing that we approach as x approaches a certain number. Alessandra, what else could you tell us about yesterday? What you did? Yeah, we looked at finding out what limits are graphically. Right, so there's different ways to find limits. You can do it numerically. You can plug in numbers really close to another number, right, and see what results you get. You can do it graphically. There's also different ways algebraically and yada yada. We'll get into more of that today. But yeah, we grabbed some yesterday. Daphne, anything else you can say about yesterday?
We talked about when it doesn't exist. So
Yeah, sometimes there is no limit. That's a thing. Totally. Gina, when does the limit not exist?
when there's a vertical asymptote.
That's one of them. Yeah, if there's a vertical asymptote, the thing is going off to infinity. So yeah, there's no limit there. Christian, what's another case where there might not be a limit?
When there's a jump.
Yeah, when there's a jump discontinuity. That's what they're called, okay? One of those things. Huey, what else? What's another case where there might not be a limit?
When I don't know what number it is. When sine over 1 over x.
Anybody remember that thing where we had the what's it called? An oscillating discontinuity. So an oscillating discontinuity is when it's moving so fast that we can't really say it's approaching anything, right? 'Cause it's just okay. Selena, what else?
Infinity is not a limit.
Infinity is not a limit, right? And infinity is unlimited, for sure. Asia? That may have been everything. I don't know. Is there anything else we didn't talk about? Yeah, that's about it. Okay. How about, can we take out that paper that we worked on, had all those limit problems all over it? And I'd like to know if anyone had a particular one that they wrestled with, or like, I'm not sure about this. Whenever I do problems, if I get it, I write the answer. But if I'm like shady, and I'm like, I don't know, I'll put a little question mark in the margin. Right, so that's a good practice. So you can say, oh yeah, there was this thing, I'm not sure about this, and you can go back and ask about it, or like ask one of your neighbors or something. So does anyone have any question marks or any problems that were suspicious? Is there anything that you wrestled with for a while and then you figured it out, and then maybe you could share that with the class because it might be helpful to somebody?
So how do you do 19 and 20?
Oh yeah, 19 and 20 on the back. Yeah, that was towards the end of class, and we didn't have time to do it, and in fact we had turned in our calculators by then. So 19 and 20, those are cases where you find a limit numerically, and you try plugging in numbers and see if the y value gets closer and closer and closer to something. So you know what we'll do? We'll end up doing a similar example that's more interesting, because 19 looks ugly.
It does.
It's not very pretty. Any other thoughts or questions about that there?
then again, it is a whole, so I don't know if it should exist.
h of 2.
HJ.
Yeah, so number 6j. 6j, if you guys want to look at that. And it says, what is the value of this function h at x equals 2? So I'm going to go over to 2, and I go up, yeah, and there's a hole there. So you were right, there is no function value. If they asked you what the limit was, you could answer that. What would the limit be? Yeah, the limit would be 2. But they didn't ask for the limit. They just said, hey, what's the function value? So nice. Keep you on your toes. Okay, if we're good with that, how about let's write our name on whatever you did your work on, and let's pass that forward. So if it's a separate sheet, you don't have to hand this in if you didn't write on it. You can hang on to this. But whatever you did your work on, write your name on it and hand it in. And again, I don't care if you made it all the way through 19 and 20 on the backside. Just whatever you got, hand that in. That would be fantastic. Yeah, hand in whatever you got. Write your name on it. If you have multiple pages, maybe write your name real quick on the top of both pages. Pass those up. And then I want to do something that I think is neat. I don't know. We'll see. See how you feel about it. I don't need to unless you wrote on it. Okay. What do you guys know about the number E?
Euler's number.
Yeah, it's pronounced Euler's. FYI.
Euler.
Leonard Euler. Yeah, some people would call it Euler, and whatever. Potato, potato. So yeah, Euler's number E. Anyone know approximately what is E equal to?
2.1. 2.3.
Yeah, 2.718281 blah blah blah. Goes forever. So yeah, it's 2.7 something. Where did that come from? Right, because you guys know pi, 3.14.
Yeah.
Circumference over diameter or something. Whatever. But E, 2.7? Huh? What's that? Anyone remember where it originated, where you first saw E? What was the first time? You're like, oh, nice to meet you. What was the first time you met E?
Natural logs?
Natural logs?
Oh.
Okay. Yeah, natural log is a log-based E.
Are we capital E or little e?
Little e.
Oh. Yeah, it's just...
Anybody remember compound interest?
Oh yeah.
Oh yeah. Oh. I knew it. I knew it. And then there was continuous interest, right?
Times e to the RT.
Yeah, per PE to the RT. Okay, let's talk about that. Because as it turns out, E is a limit. E is the limit of something. You didn't know it all these years. You're like, oh, I thought it was just a number. E is a limit.
Like a squiggly line.
Yeah. All right, so let's talk about compound interest. What was you had the amount of stuff after time t was your principal investment times 1 plus the rate of interest or whatever interest rate divided by n was the number of times you compounded your interest per year times t years times n again. Has anyone not seen this? Okay, that's cool. That's cool. So here's a So let's say you want to invest. I don't know. You invest $1,000 into some type of savings account or a mutual fund or something, and it pays an interest rate of 5%. You'll earn that kind of money. And then N, again, is the number of times you compound your interest. So if you get monthly interest, N is 12. Beautiful. So N will be 12. And let's say we want to invest this money for 5 years. So the amount of money after 5 years, we'll raise it to the 5 years times 12. And you guys want to grab calculators? Come up here and grab some of these. Use the boss.
Taylor, go get me.
And if you're going to type this in, if you're going to raise to the exponent of stuff, you need to bag your stuff. Bag those groceries. Or else it'll raise to the power of 5, give you an answer, and then you'll multiply by the whole thing by 12, and you'll get an answer that's completely wrong. But you may even write it down and think it's correct because the calculator told you the undisputed truth, and you believe the calculator always. Like the internet. Doesn't matter.
Snakes have legs. Oh yeah, snakes have legs.
Okay, so I invested $1,000, 5 years, 5% interest, monthly. What do I get back?
$1,282.84.
$1,282.84.
Yeah, man.
Groovy. That sounds reasonable. I invested $1,000, you know, $1,200, cool. All right, if I got, so monthly interest is neat because at the end of 1 month I gain interest, and then for the next month I earn interest on my original $1,000 plus I earn interest on the interest that I earned in the first month. And then the next month I get interest back, and then I earn interest on both of those interests, and then I get interest on interest, and then I get stacks on stacks, right? And it just keeps building, and compound interest. And but I'm like, well, hey, if I can get monthly interest, what if I could get daily interest? What would N be equal to?
365.
Yeah, let's try this with a 365 in it. So 1,000, 1 plus 0.05 over 12. No, over 365. I want all the interest. Times a raised to the power of, what do we say, 5 years. And it's going to happen 365 times per year. So I'm going to get interest 5 times 365 times. Many. Very interesting. So how much money do I get then? What is it?
1284.002
And how many cents?
003. No,
Just
that, yeah.
Okay. So I get another buck and change. Cool. May not impress you, but if we're talking about huge, $1 million investments or $10,000 or something, and over a longer period of time, 5 years, it would say like a 20-year investment. Those little things actually matter. It adds up. But if I can get daily interest, what if I could get interest every hour?
Oh my lord.
Oh, every minute, every second, give me the money. Yeah? So we could continue making this number higher and higher and higher and higher. And then eventually we get to this place where this is infinity, where I'm getting interest all day long. All day, every day, just interest, nonstop, right? And so that's where we get continuous interest. And you may have seen this formula. Actually, you know what? I don't want to spoil it. I don't want to spoil it. Don't tell anybody if you haven't seen it yet. So here's what we'll do. We'll look at this. We'll look at this here, and we'll see if we can rearrange this. We're going to Rubik's Cube it around a little bit and just do some smoke and mirrors And let's see, I could rewrite this. My principal investment, 1 plus R over N, isn't that the same as 1 over N over R?
Yeah.
Is that the same thing?
Yeah.
Just a reciprocal. Yeah, I know. Why would you do that? You will see soon, young Padawan. So that's legit. And then can I do this raise to the Tn? Can I instead raise this to the N over R and then raise that to the RT? Because you know a power raised to a power, what do you do with that stuff? You multiply them. So if I multiply these, the R's cancel, right? And I'm effectively raising to the power of Tn. Same thing? Thanks for making it more complicated. You'll see. Hang in there. So we want to see what happens as n goes to infinity. As I get infinity interest, right? I want all day continuous interest. So we're gonna do a limit as n approaches infinity. Now, if n is gonna approach infinity, isn't n over r also going to approach infinity? Right, because this goes to infinity. This is going to be infinity divided by, your interest rate, is 0.05 or something, whatever. But basically, if n goes to infinity, this whole thing goes to infinity. You with me?
Yeah.
Yeah, Cecilia? Picking up what I'm putting down? Okay. And then so, hey, why don't I just call n over r, let's just make that one variable. Can I just say n over r, set that equal to x? And then we can just say, that this is p times 1 plus 1 over x raised to the x to the RT. And then we're just going to look as x goes to infinity. Is that okay? Yeah, you with me? Okay. And now if I want to look as x goes to infinity, all the x's live here, right? So the p and the r and the t, these are of no consequence. These aren't changing at all as x goes to infinity. This is the only thing that's changing as this goes to infinity. And this is just leftover stuff, right? You may be seeing it come together. So let's make a table of values. Let's look at values, we plug in values of x, and then we'll look at 1 plus 1 over x raised to the power of x. And then we'll try when x equals 1, when x equals 10, when x equals 100, 1,000, 10,000, and we'll do that. So here's what we'll do. Take your calculator and type in this thing, parenthesis 1 plus 1 over x raised to the power of 1. What have I done? Oh, I'm sorry. No. You shouldn't type in the letter x. You should type in a 1 here. I'm so silly. So 1 plus 1 over 1 raised to the power of 1. Yeah, and I got 2. And now, I don't know if you know about this fancy thing. If you hit second enter, the yellow button, the amount, hit second enter, boom, it retypes your last thing for you. Shortcut. And then what I'm going to do is I'm going to change that, this 1 over 1, I'm going to change it to 1 over 10. But you guys know how if you type a thing, it like writes over top of the thing you wrote already, and then you just get mad because you got to retype the whole thing anyway. So what you do is, in my calculator, I have this right now. Go to arrow over to this thing, this parenthesis. So you got your little blinky cursor there. And then you hit second, and then 2 buttons over is delete. Second delete, and above it says INS. So that's insert. We're going to insert some stuff. So second insert, and then you can type 0, and it inserts a 0 here, and you're like, oh sweet. And then arrow over and change your exponent to 10 also. So we have 1 over 10 and then raised to the 10. Boom. What do we get? Yeah, 2.5937. Now, second enter, and then let's change it to 100. We have to insert another 0, another 0. Yeah, 2.7048, blah, blah, blah. Do it again. Make it 1,000. Oh, did you do the next one already?
Yeah.
Let me double check. 2.7181. Let's type in. We'll skip the next one. Let's go to 1,000,000. So we got 6 zeros happening here. I'm gonna add 2 zeros. Eh? You like what I'm doing? So we can type in a bajillion, and it's not gonna, right? You see how it's leveling out here at 2.71828. So at this point, this is locked in. The larger x gets, we'll just get more accurate decimals here, and you know, we can just keep getting more and more accurate estimates of E. But, so this is E. So what we're going to do is we're going to say the limit as x approaches infinity of, what is this thing? 1 plus 1 over x raised to the power of x equals E. There it is. E is a limit. And then, so as we compound our interest more and more frequently, you know, 1,000,000 times per day or whatever, more and more we do that, this term approaches E. So then continuous interest is P times this, which is E raised to the RT. Yeah? Yeah, and that's your continuous interest formula, which you may have seen before, but no one. It's possible that no one explained this E is a limit thing because maybe you weren't ready for the truth. But you're about to be seniors, said Hugh. Hang in there. And yeah, y'all are ready for this. Calculus, limits, cool stuff. All right. So what we just did is we found a limit numerically. So again, this is like Jack, you were saying, how do you do number 19 and 20? That they're saying this. They're saying plug in x values, see what your y value is, and see if it's approaching a thing. And this is clearly approaching a thing, right? But if it was like 2, 8, -7, 105, you'd be like, no. But yeah, so you can find limits. We can find limits. finding limits. You can do it graphically, which we did a lot of that yesterday, where you just look at it and say, well, what's happening from the left and from the right? We can, oh, I see what the limit is. We can do it numerically, right? We just did that. And you could also do that where just if there was a function and it said, what's the limit as x approaches 2? You could plug in into that function 1.999999. See what I mean? Because we're approaching 2. Plug in 1.999. Or plug in 2.0001. Right? Coming at it from both sides numerically. Is that cool? Both sides graphically, numerically. Sometimes you can find a limit by direct substitution. And so, direct substitution. So, for instance, if someone said, hey, what's the limit of x squared plus 1 as x approaches 1, you don't gotta be a crystal ball reader. Yeah, you can just plug that in there. Because you know this, you know what this is. It's a continuous function, it's a parabola. So you know there's no weird oscillating, you know, jump, anything. You're like, oh yeah, cool. So you can plug in a 1, limit's 2. Boom. Right? Direct substitution, numerically, graphically. You can do some algebraic reasoning to kind of conclude what a limit will be. Let's say, yeah, algebraically. Let's see if I can give an example of this. So, the limit as x approaches 1 of, we'll have this function x plus 2 x minus 1 over x minus 1. So direct substitution, you could say, hey, let me plug in when x equals 1, you plug it in here, it's divided by 0. You can't do that. So the limit is, you don't know. But then you say, hey, wait a second, what if I simplified, right, this is a rational function, and if this cancels, there's a hole there, but the function basically is this function with a hole in it. So you could say, if there wasn't a hole, so, you know, x plus 2, right, so plus 2. The function, if we graph this thing, the whole thing, it looks like this with a hole right here. Right? And so, what do you think the limit's going to be? Yeah. Yeah, you do direct substitution just knowing that there's no actual function value, there's a hole there. But yeah, you can conclude that the limit is 3. Is that okay? Yeah? Okay. So finding limits, we have some tools in our little toolbox to find a limit. Let me just throw up a gang of examples on the board and see how we're doing. And I think we're killing it, y'all. I love this, right? Because during the school year, if I'm teaching 45-minute classes, and maybe I see the students every day, maybe it's not every day, and then there's a weekend, and I feel like I can take a week or two on limits. But I think you guys are here early, you're stoked, you're ready to do this, you guys are all super sharp, and you guys are just eating it up. So I think we'll do some limits on the board, and I think we're good, you know. I think we'll quiz on this and keep it moving. So how about the limit as x approaches 0 of e to the x. So first think about what kind of method we can use. Oh, these are the people I didn't call on yet. So, Cecilia, what method do you think we could use for this? I mean, it's probably multiple right answers, but what are you thinking? We want to find the limit of this thing as x goes to 0. Yeah, can we just plug 0 right into that?
Yeah.
Is this a continuous function? E to the x, right? It's exponential. Yeah, there's nothing crazy going on there. So yeah, let's plug it in. E to the 0 is what?
1.
There. Boom. Lovely. All right. How about the limit of e to the x as x approaches negative infinity? What, Mary? What do we do with that? Yeah, because direct substitution, I mean, with e to the negative infinity, you can't just like, hey, calculator, and type in infinity, it explode, blow your arm off. So, yeah, we can't really just plug it in, but graphically, you can say to yourself, this is what the function looks like, e to the x. So as we go to negative infinity, what do you think it's approaching? 0, for sure. Or, like she said, you could type in negative of a million, and the answer is going to be 0.00001 or something. And you can say, it's going to 0. You can't fool me. Okay. Let's see. We'll do the limit. The limit of x minus 1 over x as x approaches 0. Who's that? LA. Direct substitution?
Yeah.
Just plug that 0 into the denominator? Yeah, we can't do that. It's not a thing. So what are we going to do? Because if you get it undefined, that doesn't necessarily mean the limit doesn't exist. It just means that your method didn't work out. So, because there might be a limit there, I don't know.
I mean, algebraically, but still, even if you plug in, like, if you use 0, it's going to be negative 1 over 2, so.
Yeah, we can't, like, cancel that.
Cancel it out.
Okay? Yeah, you want to graph it?
Yeah. Giraffe.
Giraffe it, bruh. Okay, well, what's that going to look like?
That's not exist.
Well, so that's a rational function.
Vertical as between 0.
It's got a vertical one at 0, because the denominator is 0. And then the top and bottom are equal in degree. So the horizontal is going to approach the ratio of lead coefficients. Horizontal at x, y equals 1. It's going to look like this. So as x approaches 0, what's the limit?
It's fine. That's not exist.
Is that way?
Yeah.
Oh no.
I'm telling you, these rational functions are silly. Is it? Why is it the other way? You mean like this?
Yeah.
Yeah, okay. Whatever. Fine. But the point is, Hele, what's the limit as x approaches 0?
Infinity?
Yeah, so from the left side of 0, it's going to positive infinity. From the right side, it's going to negative infinity. What do we call that?
So it's not infinity.
Correct. Did it? Does not exist. 2. How about the limit of, let's do that same function. That was fun. But we'll say as x approaches 1, And Janice, what's the limit as x approaches 1? And I probably drew this totally inaccurate. But so what method could you use with that?
Look at the graph.
We could absolutely do that. I wouldn't rely on this graph. I would use a better graph. But is there an easier way?
Yeah.
I mean, direct substitution is 0 over 1.
Okay, is that a problem? I plug in 1, we get 0 over 1. What's 0 divided by 1? 0, that's a thing. I bet you the limit's 0. Direct substitution. And as, oh look, I drew it. I'm nice. I'm nice. Yeah. Okay, what else? Let's do the limit of, same thing, as x approaches infinity. Andrew.
I guess graph it.
Yeah, that'd probably be the best method. Yeah, direct substitution isn't all that great. I mean, you can plug in numbers and stuff, but yeah. So what do we know about the graph? Even if we don't have a fancy calculator, we do know something about as this thing goes to infinity.
It goes to 1.
Yeah, do you see it, Andrew? Yeah. We have the horizontal asymptote.
Whoa.
It's approaching 1.
Yeah.
Yeah. Cool. And how about, ooh, this is fun. Of sine of x over x as x approaches 0. Leslie, what method do you think would be good? Let's see, direct substitution. If I put in a 0 here, I got to divide by 0, and bad things happen. Algebraically, I don't know if I can like cancel or. Yeah, graphically might be our best. I mean, we could try plugging in. So graphically or numerically are probably equally decent options. Numerically, we would plug in 0.00001, and then we would plug in negative 0.0001 to see what's happening on the other side. Or we could let's graph it just for funsies. Type that thing in your calculator and then zoom 7. It's probably a good thing to do. Zoom 3. It's a pretty neat graph. And this BT dubs, this is called a sync function, sine of x over x. It's used in digital signal processing. When you talking to your phone, and it takes that analog signal of your voice and it breaks it down in a bunch of ones and zeros, basically turns it into digital stuff, sends it across the airwaves, and then it reconstructs the sound of your voice on the other side. They use this in that process. The sync function is pretty cool, man. You guys see it on your graph? It looks something like this. Depending on your window, right? But it's a sinusoidal, so it's a wave, but it's dividing by x. So as your x gets bigger, you're dividing by bigger and bigger stuff, and so it's becoming a bigger and bigger fraction. So the wiggle gets smaller. We're getting smaller and smaller amplitude on that wiggle. What seems to be happening though, as x approaches 0, so you can trace and like go a little bit to the left of 0, a little to the right of 0, what's it look like it might be approaching? Oh, this was Leslie's question. I don't want to steal your thunder. What is the limit as x approaches 0? Because if we type in x equals 0, there's a hole there, isn't there? You can't just type in 0. But you have to get close to it from either side. What do you think the limit might be? Is that what it is? Can you see it on your calculator?
Yeah, it almost looks
And oh yeah, you got 0.99 and stuff? Okay. Yeah. Approaching 1. You guys okay with that, with using your calculator? You guys know when you hit the trace button